Alrighty guys, here we go. We're going to talk about some story problems. So we're really taking in 2 days worth of stuff here. So we need to keep in mind that we're going to be writing equations because we're going to be reading a story, writing the appropriate equation for it. However, it's going to be a little bit more difficult because you're going to have to write 2 equations. And because it's 2 equations, you're going to be solving for 2 unknowns, and you're going to want to solve it by using those skills that we talked about previously, substitution or elimination, unless you really want to graph, because me too. So I'm actually going to jump to the end here and do this very last example where we talk about money and how many. So the reason I titled this money and how many is because generally these problems have like 2 equations, one of which is all about the money and another equation is all about how many. And so as we're kind of reading through this, we kind of can't use the cheaty way that we were writing equations from yesterday where it was like, okay, how many numbers do I have? 2 numbers or 3 numbers? That sort of helps, but because there's 2 equations here, there's going to be a lot more than just 2 or 3. And sometimes there's not even going to be like 4 or 6 because they're a little bit hidden. So if we read through this one, we got a store sells small notebooks for $8 and large notebooks for $10. If you buy 6 notebooks and spend $56, how many of each size notebook did you buy? So lots of different ways to think about this question here. I always like to think about the question at the end. How many of each notebook did you buy? So the thing that I don't know here is going to be like my variable. And I don't know how many small notebooks and how many large notebooks. So we might decide right now that S is going to stand for small notebooks and fancy L is going to stand for large notebooks. And those are the things that I don't know because that's what they're asking me. Now, another thing that I think about too, if I read that first sentence again, I notice, so they're talking about small notebooks being $8 for every single one of them, and large notebooks for $10, every single one of them. And so these are both sort of over and over again numbers, and I'm doing kind of both of them at the same time. So this is a lot like we talked about yesterday when we were talking about standard form. The standard form of an equation is so nice because it has 2 over and over again numbers for 2 different variables. So every time I buy a small notebook, it's going to be $8. And every time I buy a large notebook, it's going to be $10. And I'm buying all the notebooks for a total. And now these are all prices. And so hopefully it makes sense and feels good that I would also want to pick the other dollar number to be my total. So I spent a total of $56. Now the thing is, this one equation is not enough for me to be able to solve how many small and large notebooks. I need a second equation, and luckily I have another number that says I bought 6 notebooks. But sadly, it's only one number. And so for my other equation, I only have one number that they've given me. However, if you think about it, you bought a total of 6 notebooks. So really, I do have another standard form thing where my total is 6. And the things that I'm adding up over here are small notebooks and large notebooks. I'm just not considering their prices anymore because we're not talking about price. We're talking about how many. So we got dollar bills and how many. So those are our 2 equations. Now, lots of different ways we could solve it. We could do substitution. We could also do elimination. I kind of like elimination. It feels fast. I'm just going to multiply everything here by -8 because then my S's will eliminate, and 8 was a smaller number. I could have picked -10 as well. So if I do that, I'm going to have -8S minus 8L equals -48. And then I'm going to add my top and bottom equation, so I'm kind of ignoring that middle one. And so I'll have 0 S's, 2L equals 8. And so to solve for L, I'll find that there are 4 large notebooks. And once I know that there are 4 large notebooks, I feel like it's pretty easy to figure out the small notebooks because we bought a total of 6. And so if there are 4 large, there has to be 2 small. Okay, so another one sort of like this. If you have $200, you have $200 that you just got for your birthday, and your favorite store has jeans on sale for $25 and a dress on sale for $50. You would like to get 6 items of clothing. How many pair of jeans can you get? Oh, now how many dresses? I don't know how many dresses. Maybe I just care about jeans though. But I think jeans and dresses, like how many of them, is the thing that I don't know. Also, thinking about the last one where I had a money equation and a how many equation, I see 3 money numbers. So I can do maybe that standard form equation thing again, because I have a total of 200 and I can spend $25 for every pair of jeans that I buy. So like 25 for every pair of jeans and $50 for every dress. Now I know I'm not going to buy a dress, but I think this is how I would write my money equation. And then the only other number that I have is that I'm going to buy 6 items of clothing. So again, 6 items is really the total here. So a total of 6 items, and some of those items are going to be jeans, and actually none of those items are going to be dresses, because I guess that's what they're telling me. I don't know. I'm just going to solve it. Like how many jeans and dresses? I don't know. How many pairs of jeans can you get? Well, I feel like if I just want jeans, I'm going to put 0 in for dresses, I guess. So if I got, well, then that's just 6 jeans. I don't know. I'm just going to solve this using elimination. I'm going to multiply everything by negative 25 so that my j's will eliminate. So if I do negative 25 times 6, that's going to be negative overall. And if I have 6 quarters, I have $1.50. And then negative 25j plus negative 25d. I don't know why I put the plus negative. That makes me feel real uncomfortable, but it's already written down, so I can't undo it because I did it in pen like a dummy. Anyways, if we combine these up, 200 and negative 150 is 50. 25j, negative 25j, no j's. 50d minus 25d is 25d. So I can get 2 dresses. And if I buy 2 dresses, then that means I can get 4 pairs of jeans because I got 6 items total. I think that's what it wants. It just doesn't care how many dresses. I'm pretty sure, though, that's what I intended on that question there. Okay, so then the other ones that we talked about today was all the way back at the start here, our distance equals rate times time stuff. And in distance equals rate times time, I always had like a little mini baby heart attack. I think it's because I didn't realize that kilometers was distance. And like we always talk about kilometers rather than like feet or miles, because apparently, you know, we got to use those American units. Can't be using those European units. Come on. Anyways, but also when we had a distance equals rate times time formula, we were kind of lying to you when we said that this was actually the formula. Because this is not accounting for friction when I drive, or like the air current that is maybe blowing against me as I'm flying, or the water current as I'm like paddling down the river. All those things might make me slower or faster, and it's important that we account for those. So if we try this one out here, we have that Connor is flying an airplane. He flew his airplane 900 kilometers in 5 hours with the wind. He flew 700 kilometers against the wind in 7 hours. Find the rate at which he flew in still air. So if the air is not moving, like how fast is he actually going? So there's no air. How fast is he? And then what is the rate of the wind? So now that the air is back, how fast is it going? So we kind of have two different distance equals rate times time things. One of which is when I went 900 kilometers in 5 hours with the wind. It is so key to understand that with the wind is going to affect my speed. And so when I think about my distance equals rate times time equation, my speed will not just be rate. Because I'm going with the wind is going to push me faster and make me go faster. So the rate that I'm flying plus the rate of the wind is truly my speed. And then I multiply by time still. Now another flight that I took that was 700 kilometers, but going against the wind took me 7 hours. That is going to have to be a separate equation, although it's very similar. So distance equals rate times time still. However, that rate is not just going to be a rate. That wind is pushing against you, making you go slower. So to slow your speed down, I would subtract the rate of the wind off of it. So we have our two equations. We just have to plug in the numbers that we know and then solve for the things that we don't. We're not going to know two things. We do, however, know distance and time. Okay, so for this top one, in place of distance, I can put 900 equals r plus w times 5. And then for this one down here, I can write the distance in 700 and then r minus w times 7. And the very tempting thing here, whenever I see parentheses, I feel like I want to distribute, but don't distribute. Because I also notice it's set up real good for elimination. But if I distribute, I'm going to muck it all up with my numbers. So instead of distributing, I'm going to divide the 5 on both sides. And so this brand new equation now will be 180 equals r plus w. No parentheses needed because I divided the 5 away. And similarly on the bottom, I'm going to divide that 7 away to not muck it up. So 100 equals r minus w. And now I really am set up perfectly to eliminate, because if I add these up right now, I'll get 280 equals 2r, no w's. And so the rate that I am flying is 140 kilometers per hour. And then pretty easy to look back right here and notice that the rate, 140 plus something, has to be 180. That something, which is the rate of the wind, is 40 kilometers per hour. Okay, let's try another one that's very similar. In Thompson Creek, now we're rowing. We're not flying, we're rowing. Brittany can row 48 kilometers downstream in 4 hours, but it takes her 6 hours to row the same distance upstream. Find the rate that she rows in still water and the rate of the current. Now, I really do use the same two formulas. I just need to figure out like which distance in time needs to go with the plus and which distance in time needs to go with the minus. So if we take a little notice here, I can row 48 kilometers downstream in 4 hours. So if I'm going downstream, that means I'm going like with the current. Downstream means I'm going to be going faster. So this is my plus situation. But it takes her 6 hours to go the same distance, but upstream. So upstream is slower. It's working against me now. And it is the same distance. It kind of feels like I only know one number there, but it's the same distance. So I actually know that it's 48. So if we write our equations, we got our distance is 48 kilometers. R plus W times the time, which was 4 hours. And then down here, same distance, so 48 again. But now we're going against or upstream, and it took me 6 hours. It took me longer. That makes sense. And so just like the last one, I'm set up real good for elimination as long as I don't distribute. So don't divide it away instead. So now I'll have 12 equals R plus W. And down here we'll have 8 equals R minus W. And we can add up right now. So we'll have 20 equals 2R, no W's. So the rate that I am rowing is 10 kilometers per hour. And the rate that the water is pushing on me must be 2 kilometers per hour because I saw that my rate plus the water was making me go 12 miles per hour. So hopefully those can help there, guys. And we're going to do lots more story problems tomorrow, and I'll see you then.